Hello, my name is Noah Joyner, and my project is titled A Systematic Approach to Galerkin's Method. I've been doing this project under the mentorship of Dr. Robert Adams at the College of Engineering at the University of Kentucky. So for a quick overview of my presentation, I'll be starting with my introduction / background information, then moving into my programming goal, then talking about the methodology and mathematics, moving into my results and some discussion / conclusion, talk about the applications of approximation theory in Galerkin's method, go into my acknowledgements, talk about my references, and then my email will be supplied if you have any questions. So to start off, my project deals with something called approximation theory, and this is essentially complex mathematical theory that involves approximating complicated functions, typically done by creating a summation of other functions that approximates the data sets of the original functions. So accuracy is typically dependent on degrees of freedom or the range that we're looking at. And so obviously when approximating the function, we want to have the lowest amount of error possible and the highest amount of accuracy. So maximizing your degrees of freedom and range can be beneficial in approximation theory. And error can be calculated using a variety of different methods. Typically the way you calculate error is dependent on the way that you approximate the function originally. And the most basic and universal example of approximation theory is a Taylor polynomial. This is a method of approximating complex two-dimensional functions, typically sinusoids, and breaking them down into, creating a polynomial, creating a combination of polynomials that approximates the data values of the more complicated function. So in modern times, it's a little less useful to by hand approximate a sinusoid because we have a computer that can do that, can accurately graph that in a blink of the eye. So there's less use for traditional approximation theory. So modern approximation theory has become useful when it comes to really intensely complex functions as well as higher dimensional functions that even a computer would struggle with graphing and calculating. So there are methods to using this higher levels of approximation, and one such method is Galerkin's method, which is what I've focused on for this project. So Galerkin's method. So there's two main steps that we need to look at for Galerkin's method. The first is breaking the original function down into its bases, and the second is taking all the bases and running them through the function for Galerkin's method. So there's two ways that we will be calculating the bases. One is using a Lagrange polynomial, or the other is using something called spectral element analysis. And the method used is dependent on the dimension of the original function that we're trying to approximate. So for the Lagrange polynomial, that's only for functions that have a dimension of 2 or two-dimensional functions, whereas spectral element analysis can be used to find the bases for anything higher than that. So my programming goal is to create a universal program that can apply Galerkin's method to approximate functions using MATLAB. And I've chosen MATLAB because it has great graphing utility and mathematics utility and matrix utility, which has come in handy for this project. And the goal is to maximize my efficiency and maximize accuracy, both to the best of the ability of the program, and then create a GUI for specific analysis of the results depending on the user's application. And a GUI is a graphical user interface. So to start off with the mathematics and the methodology, I want to look at the Lagrange polynomial. This is how we determine our basis functions for two-dimensional functions. So as you can see, the Lagrange polynomial is just a combination of a bunch of other polynomials. In this case, they're referred to as L polynomials. So as you can see, you will have, depending on the data set you are looking at, depending on the data set you are looking at, you will have that many, however many points you have, you'll have that many L functions. And so you can refer to each L function as L sub whatever data point number you're on. So if we're looking at L sub k, which is just a sample L function, that would be equal to the numerator, which would be the product of all x minus x sub i's except for x minus x sub k. So x sub I would be, or it would be from x sub 1, so the first data point, to whatever your maximum is. And then the denominator of Lk of x is the product of all the x sub k's minus x sub i's, except for x sub k minus x sub k, which would obviously be 0. And so once you take all those, if you add them all together, you end up with your Lagrange polynomial. So the other way that we determine our bases is using the spectral element analysis. So spectral element analysis is based off something called finite element analysis, which is essentially when you take a mesh or a complex function and break it down into a finite kind of basis or shape. This is typically done in a triangle. Yeah, you would apply the triangle all over the face of the mesh to see how it would break down, how many of these elements would you need, stuff like that. Now, spectral element analysis is very similar, but it's designed using a higher dimensional basis than just a two-dimensional triangle. So in my specific case, I used an initial nodal tensor product Lagrange basis as my original basis that I applied to the rest of the function. And once you calculate this original basis, you can use all the remaining bases can be calculated orthogonally. And so essentially what that means is that they're perpendicular to the original nodal tensor Lagrange basis. And so they aren't actually perpendicular because they'll exist in a higher dimensional plane, but it's the law of perpendicularity applied to higher dimensions. So once we have generated our bases, we'll put them in a matrix and we will run it through this Galerkin's method formula. And the Galerkin's method formula is the integral from b to a of the basis function that we're looking at times the linear differential operator plus the original function that we're looking at. And so what this gives you is something called the alpha coefficient. And the alpha coefficient, essentially, if you take the alpha coefficient and you multiply it by its basis and you add every other alpha coefficient and every other basis, if you add them all together, that's how you end up with your original function, or the approximation of your original function. So the final goal is our alpha coefficients. So now for some results, I'm talking about efficiency first. So this process was successfully applied into MATLAB, and the efficiency of the program was big O notation of n to the d times the log of n, where d is the dimension of the function. So as the dimension of the function increases, it does take longer for the approximation to, or for the Galerkin's method to apply itself and for the program to run. But if you compare that efficiency to the efficiency of just generating the data for the function without any approximation, that would be O notation times the dimension times into the dimension. So that increases exponentially of how much time the program takes versus when we approximate it, the dimension does not make it increase so much. So as the dimension increases, approximation becomes increasingly more efficient over data collection. And now talking about error. So estimation error can be controlled and mitigated when it comes to lower dimensional functions quite easily. We can just take a look at the range that the user wants to look at the function over, and you can just make that as large or as little as you want, and you can kind of control your error in that regard. And the more data points you plot, the less error there's going to be. And so, yeah, so we can just apply a Lagrange remainder when it comes to that case to calculate the error, and minimum error should be expected because it's based on the initial degrees of freedom, which is set by the user. Now, when it comes to spectral element analysis, the way to calculate our error for our bases is something called an a priori error estimation, and that's a lot less predictable and a lot less accurate. In fact, it itself is an estimation. It's an estimation of how much error there could be. It's not even actually how much error there is. So if you look at this graph, you can see that as the degree of polynomial space increases, the estimated error from the a priori error estimation drastically diverts from the actual calculated error of the approximation that was created. So actually applying a actual error estimation to the higher dimensional functions is extremely slow and a complicated process. So a priori error estimation is preferable when it comes to lower degrees of polynomial space. And practically, you're not going to be running 15 or functions that exist in 15-dimensional space through the program, because you're not going to functionally be looking at anything like that. So practically, it's not a big deal. But in theory, as we increase degree of polynomial space, a priori error estimation becomes less accurate. So trying to minimize error while still keeping the program relatively efficient is very difficult. We could focus at making the program more accurate when it comes to higher dimensional functions at a risk of efficiency. And so I'm trying to keep the two balanced. So that's why I'm currently using a priori error estimation. So it has been shown that using a Galerkin's method to approximate functions can be more efficient than actually calculating these functions when it comes to higher dimensional functions. And so that's very useful. So let's talk about a few applications of the program. A big one is computational electromagnetics, specifically looking at aircraft or marine craft message and seeing what electromagnetical forces are acting upon these crafts on the day-to-day basis. So like a submarine, you could be looking at radar or any kind of other electromagnetic force that may be sent towards the aircraft, and you can use these calculations to quickly get an idea of what forces are acting upon that, what that means for the trajectory of the craft, stuff like that. And you can approximate that and do that very quickly to a pretty high accuracy and efficiency. Another application is simplistic simulations, so kind of like graphical simulations if you're trying to render a cube flying through a, whatever. You could do that a lot faster with Galerkin's method. You could plot out the pathing function and it could approximate it and do that a lot more efficiently and render the simulation a lot more efficiently than if you were rendering it how you typically would. More applications, just looking at more than 3 variables. So if you want to look and compare 5 variables, if you create a function that plots all 5 variables in relation to each other, you can use this program to break it down to its parts. The GUI allows you to pull different basis functions scaled by their alpha coefficients to kind of see what two parts may look like posed against each other. So if you're comparing 5 different variables, you have x1, x2, x3, x4, x5, you can look at graphs for x1 versus x2, x2 versus x3, x1 versus x3, and so on, and kind of getting an idea of how all the variables compare with each other. And then just breaking down higher dimensional functions to see trends. So higher dimensional mathematics is something that math is looking into as a field right now, and breaking down higher dimensional functions and looking at trends of them and being able to visualize them better may be important in theoretical math in the future. So I want to give a shout out to my mentor, Dr. Robert Adams, as well as his associate, Dr. John Young. I also want to thank the University of Kentucky and the Kentucky Young Research Program, Ms. Karen Young and the MSCC program, and family and friends for rides to lab. I also want to thank MATLAB for having a fantastic collection of any information you need to know about the MATLAB language, functions, programs, all that stuff. And here are my references. And if you have any questions, you can email me at knowitall2002@gmail.com. Thank you.